All right, well, thanks for the invitation to speak here. So in my lab, we use many different types of models with different fidelities, different modalities for cardiovascular modeling. So the goal of this presentation is to just share with you some of our experiences and rationales for selecting and using the different types of models. So this talk will be very high level, which I think is suitable as a first talk after lunch. I'm not as creative as Joan, who apparently does backflips to keep people awake. So I have to use other strategies. All right, so the way I like to think about this is where a specific type of model falls on this map. So you got fidelity, which is how closely you could capture the physics and the cost of construction. And then you have the scope, goes anywhere from just looking at a local region, small portion of the cardiovascular system, or including microvasculature to the global region and extending to capturing heart response, so cardiac feedback and things like that. So for example, computational fluid dynamics typically used to look at a small region of blood vessel and can offer pretty good fidelity, and it gives you 3D information, the velocity, pressure, wall stress, and so on. Now, experiments or in vitro model, on the other hand, can offer a little bit higher fidelity. People use experiments to validate CFD simulations. And you could also extend it to a more global scale by using things like a Wien-Kessel impedance module to capture all of vasculature. Now, lump parameter network, or LPN, on the other hand, it's a low fidelity, and so you don't get any spatial information. It doesn't produce any pretty pictures. You just get pressure and flow waveforms. So I present results from the LPN, and people doze off. But the good thing about this model is that it's very cheap, and it's easy to basically you could incorporate a lot of mathematics into this model very quickly. You can have all sorts of heart models you could put in there, which gives you cardiac feedback. And you have things like 1D models that are somewhere in between. So these are just a couple commonly used types of models. And you can determine the level of fidelity that you want in your research and go up on this scale and all the way up to using physical experiments. Or if simplicity and scope is what you're looking for, you could also go all the way to using a lump parameter network. So today we're going to take maybe a closer look at these two being at the outer edge of this map. So you could have a high fidelity or a wide scope. The major advantage of using physical experiment is that you could physically include the actual device or materials that you want to study in the experiment. And so this allows you to directly investigate their interactions and be able to capture the relevant physics. So I'll briefly mention two examples where we used physical experiment. And so here's a Jarvik 2000 blood pump that we hacked. We modified their controller with the permission of the engineering team at Jarvik, who loaned us the device. And so we wanted to characterize its new behavior in the hacked version. And so this is pretty standard. We put in the flow loop, be able to characterize pressure and flow at different RPMs. And here's another study where we're trying to make a new type of blood pump, which you can basically wrap around the outside of a blood vessel, and it will kind of squeeze like this to pump blood. And so this, requires no blood contact, and that would be an advantage. And so we have a couple of prototypes that we wanted to test. And so we have a flow loop where we can directly try to mimic the operating condition of this device and be able to study the physical characteristics. Now, we could model all of this with mathematical models, but the reason that we used experiments is because the ground truth can only be revealed when you actually have the device in there and you can directly study it. Now, the limitation of in vitro models is that you typically need to prescribe some kind of flow condition in your circuit. And so it's usually pretty difficult to get direct cardiac feedback with in vitro models. So that brings us to LPNs. Now, LPNs it's very easy to implement any kind of behavior that you can approximate with a mathematical equation. And so that allows you to put things like heart models in there. That's very easy to do. It's very cheap to run, so you could run a whole bunch of them if you need to. And it's light and portable, which offers a wide usage possibility, which I will show you a quick example. And for those of you who do CFD and multi-scale models, you know that the LPN can provide boundary condition, which is basically determines what the flow looks like in your model. And so that's the importance of the LPNs. So I'll show you an example where we use the LPN. This is a study where we look at cavopulmonary support for Fontan patients. So these are patients who are missing the subpulmonary ventricle. And so the idea is that if we substitute this missing ventricle with the pump, this might potentially help improve their physiology. So the problem is currently there are no existing device that's commercially available that is designed specifically for this purpose. And recently we've shown that if you were to use the left side blood pump for this application, it has its own risks. So the goal of this study is we want to answer the question, if we want to design a blood pump specifically for this application, what would the design requirements be for this device? And there are two different types of physiologies and two different types of implementation that we're looking at here. And so the approach that we took to answer this question is to use an LPM model to be able to capture a wide range of clinical scenarios. So we ended up creating 1,245 patient cases that exhibit a combination of different physiologies that spans across plus or minus 2 standard deviation of what's clinically observed out there. And so here, if you look at the blue, that's the plus minus 2 standard deviation of clinically observed parameters that we found in literature. And then if you look at all of our simulation together, that's the range. So we want to capture all of those scenarios. And then for each patient case, we want to simulate different kinds of pump input to try to approximate what the physiologic outcome would be. So we ended up running a total of about 90,000 simulations. And in these simulations, for each of them, we look at the pressure and the flow that's going through the pump in those cases that created a favorable physiology. And then we conjugated them to come up with these regions for the different type of assist scenarios. And so basically this can help to serve as a guide for the design requirement for such a device. So the reason that we choose to use LPN is because, well, it's good for running a large number of simulations is what we need to do here to capture different type of patient cases. And here's another quick example is a collaboration with a couple of colleagues, Richard Figliola and Alison Marston here. So we created a app for running patient-specific simulation that can run on an iPad. And so this is basically just a proof of concept to show that if you use a light and portable models like these, you could potentially have a tool that can offer real-time clinical assistance. So as we see, that LPN are cheap, and they can provide potentially a lot of value. Now, from talking with people from industry and some from academia, a lot of them express that the barrier for them to use the LPN is they don't know what parameters all to set for the components in the LPN. And there are quite a few components in the LPN circuit. And if you look into the literature, you'll find actually quite a few papers that basically use numbers directly from the classic Snyder and Rideout paper in 1969, which basically represents one single patient. So what we see as a need in the field is that we need to have some kind of generic baseline model that people can use as a starting point. And so that's what we're working on right now. And the approach that we're taking is we're doing some meta-analysis to try to compile all the data that link the type of patient that you have and what kind of physiology they have. And then we're doing some regression machine learning to try to make that link. And then we're doing optimization to figure out what the LPM parameters should be. And so in the end, the product that we hope to have is to have a protocol. Basically, you want to model some kind of patient, and then we'd be able to tell you what parameters in the LPN that you can prescribe to hopefully make this easy to use for people. Okay, so we've talked about these two approaches that can offer a high fidelity or a wide scope. Now, we can get the best of both worlds if we combine them in some sort of multi-fidelity, multi-modality model. And that's what we've done. And so this is a technology that we recently developed called the Physiology simulation coupled experiment. And what this is basically we came up with a coupling scheme to be able to directly connect a physical experiment to a computational physiology simulation. And so what this gives you is basically you can have the fidelity of a physical experiment in the part where you need it, and also at the same time have the scope that the LPN is able to offer. And so, for example, you can use this to directly test a medical device, but in the context of patient physiologic feedback. So this it was published earlier this year in JBME, and I'd be happy to talk to you more about it if you're interested in knowing more about this technology. So just to summarize, these are the principles that we apply in the lab for model selection. So we try to identify the cheapest model that can capture the physics that we need, be able to return the quantity that we're looking for, and include the scope that are relevant. And then next, we think about practical constraints. Can we afford to run or construct these models, and do I actually have enough data to do so? So for example, if I wanted to construct a geometric model, then I would need some kind of anatomic data. And then finally, we love to combine models to get the best value versus complexity. And so we want to use the high fidelity model only for the small region where it's absolutely necessary, and then replace everything else with the low order model that is cheap to run. So here are some references I'd be happy to share, and I want to acknowledge the students and the collaborators that contributed to those projects, and as well as funding sources. Thank you.